Hello, so you should have had your feedback from your results tables and graphs so far. Generally, the results tables look pretty good. The graphs look pretty good, but there were common things that appeared across nearly everybody's work. First of all, a lot of people had all their points plotted up in one little corner of the graph. So if you had a little corner of the graph, all your points were up there. You will lose a mark if they do not fit more than half the available graph space. So do not forget that. Secondly, plenty of people didn't actually use little dots with circles for plotting the points. That's the preferred way of doing that. So make sure you do that. Another thing is, plenty of people only had 3, 4, maybe 5 points. Make sure you've had as many points as you can reasonably take. Because if you've got a small number of points, you cannot, with any great reliability, tell what the trend is. So, for example, 3 points. Is that a curve? Is that a straight line? Or one of those anomalies? We can't really tell. But if you've got a lot of points, it becomes a lot more obvious what's going on. But let's move on. You've got a curve graph, and we find it very difficult to analyse curve graphs. And there are a few different graphs that whenever you see, you should instantly start to recognise. At GCSE, you would have known that if you saw a graph like that, you would know that whatever's in the y-axis is directly proportional to whatever's in the x-axis. And you would have seen plenty of graphs like that. F equals MA, V equals IR. And you would have linked those to an equation. Because that's following the equation y equals mx. You're also familiar with graphs like that. Y equals mx plus c. Not directly proportional because the line does not go through the origin. One that you would have seen occasionally, could have seen occasionally, is a graph that looks like that. And that's where y equals kx squared. So there's this squared relationship. But we haven't got any of those graphs today. The graph that you plotted, a lot of you plotted straight lines, and that was reasonable, bearing in mind that you had a limited number of points. But your graph should have looked something a bit like that. And certainly the one that I did looked a bit like that, and there were a few of you that did that. And that looks possibly, so y equals k, and the k is a constant, we don't know what that is yet, root x. And that's what we're dealing with today. We're dealing with something where whatever's in the y-axis is proportional to the square root of whatever's on the x-axis. So let's think about that a bit more. So we had a graph of time period against length. And it looks a bit like this. Now, none of us plotted points that could legitimately draw a graph going down to the origin. But I think that's something we're going to assume is happening here. If you have an infinitely small pendulum, it should be moving infinitely quickly. You can't really test a pendulum with zero length. So, if we want to turn this into a straight line graph, what can we do? Don't forget that this time I've said that y is proportional to the square root of L. So, in other words, t is proportional to the square root of L, which means t is equal to some constant times the square root of L. Now, if we want to put that into a straight line graph, and don't forget a straight line graph is in the form y equals mx, what we could do is plot t against the square root of the length. And if that relationship is correct, we should get a straight line through the origin. I don't really like taking the square root of things. Another way of doing that is to square both sides. If the time period is equal to k times the square root of L. If we square all that, t squared equals k squared L. And if we plotted a graph of t squared against L, we should get a straight line through the origin, and the gradient of that line should equal k squared, whatever k is. We don't know what k is just yet. So what I want you to do today is to take your results from last week. Don't forget, you already had length in meters or centimeters, whatever that was. You had your time for 10 oscillations in seconds, and you had 1, 2, 3 and an average. And then you had the time period in seconds. I'd like you to add an extra bit, t squared, and the unit of that, with time squared, the unit's also going to be squared, s squared. And I would like you to plot your length and your time squared. So time squared on the y-axis, length on the x-axis. Hopefully you should end up with a straight line through the origin. If you only have 3 or 4 points, maybe even 5 points, you might need to go and take more results. If you cannot get it to work, you could use the results that I have put online already. So I would like you to plot the graph and find the gradient of that line. And then next week we'll have a look at what that gradient represents. Your gradient should have a number. It should also have a unit. So please make sure that you include the unit of your gradient. I know you've been doing units with Mrs. Gregg in Unit 1, and we can use units to help us identify what this gradient actually represents. And maybe you might start to recognise some of the units that are appearing. Please get in touch if you have any questions.